Hey everyone, welcome back to Engineering Education. For this next problem, we have our first z-transform problem. And here we're given the difference equation. X of n is this third order difference equations of Kronecker delta functions with different coefficients. And here we're asked to find the z-transform of this equation. So as always, pause the video, give it a shot, and we'll go over the answer in a bit. So to solve this, we need to know what this Kronecker delta function is. And essentially, it's a function that is equal to 1 at n is equal to 0. And this is not to be confused with the Dirac delta function. So Kronecker delta is used with discrete systems, and the Dirac delta, which is infinity at x is equal to 0, that is used in continuous systems. So this here would be 1. And so the z-transform x of z is equal to the z-transform of x of n. And since the z-transform is linear, we can take the z-transform of each of these terms individually. So we can start off with the first one. We're looking for the z-transform of 2 Kronecker delta of n. And we can pull out the 2 since it's a constant. And we get the following. And in order to solve this, we can go to the FE handbook where we have a table of z-transforms, and we can find the z-transform of this delta function. So here in the FE handbook, page 206 in this version, we have a section on difference equations, right here. And we're given what a first order looks like, what a second order difference equation looks like, and the definition of a z-transform. And this is going to be very important, especially for those z-transforms that you'll have to derive. So if we go up a little bit, we have a table of commonly used z-transforms. And there is our delta function right there. And we're told that the z-transform of our delta function is equal to 1. So we'll go back to our sketchpad here, and we get that the z-transform is 1, so then this equals just 2. Alright, so 2 times 1 is 2. And so that's the z-transform of this first term. And now we need to find the z-transform of the second term here, n minus 1. And just as before, we can pull out the constant and then just take the z-transform of the delta function at n minus 1. But if we go back to our chart, we see that there is no direct z-transform for this shifted delta function. And so what we have to do is either you memorize this or you derive it. And we derive it using the definition of the transform right here. And so that's what we're going to do. We're going to derive it once, we'll see a pattern, and then we can easily do the rest of them. So going back, we're going to do a side note here. And so I'm going to write down the definition that we saw on the previous page. Only instead of f, I'm going to use x. X of z is equal to k is equal to 0 to infinity of x of k, z of minus k. And so that's the definition of the z-transform. And then we're going to try to find the z-transform of the delta function shifted by an arbitrary position that we'll call n0. So we want to find the z-transform of delta function of n minus some shift n0. This will be n. And so we plug it into the Z transform, and then you get the sum k is equal to 0, delta function of k minus n0, z of minus k. So if we look at this, the delta function is equal to 0 at all values of n except at n is equal to 0. And so when delta of 0 is equal to 0, that is the only time it has a value, and it's 0 otherwise. And so even if we are summing up from 0 to infinity, there's only one value where the delta function is non-zero, and that is at n0. So when k is equal to n0, whatever n0 may be, the delta function takes a value of 1, and then we get the following. So it'd be 1 z of minus n0, which is z to the power of negative n0. And so that is the z transform of any delta function shifted by n0. And so we can go back to our problem here, and knowing this property, we know that this is 3 times, now we're shifted by 1, and so this is z to the minus 1. And now we can solve the rest of them. The z transform of 5 delta n minus 2 is equal to 5 z to the minus 2. The z transform of 2 delta n minus 3 is going to be 2z to the minus 3. And now we can put all these together. X of z is equal to 2 plus 3z to the minus 1 plus 5z to the minus 2 plus 2z to the minus 3. And that is the z transform. And so the important thing to remember is I would memorize this derivation that we just did here. This is not going to be in the FE handbook, and it's something that either you're expected to know how to derive or you're expected to memorize. And the other thing hidden in here is the linear property of the z transform, where you can break up these sums into individual z transforms, which are easier to manage, and do that. The other property we used was the time delay property. So more formally, and I don't think this is also on the FE handbook, but another property that we used was the time delay property, which simply states that some x of n minus 0 z transforms into z to the minus n0 z transform of x. And so our z transform was the delta function, so this actually became 1, and then we used this property. So I hope you guys enjoyed this video. If you did, please leave the video a thumbs up, and I'll see you guys in the next video. Until then, enjoy engineering.